Okay, there's only one kind of calculation in the last module. It's to balance a nuclear reaction and to calculate the Q value to find whether it's an endothermic or exothermic reaction, whether energy is released or energy is absorbed. So what's the Q value? The Q value is equal to, by definition, the mass of the initial constituents minus the mass of the final constituents times C squared. So let's look at our first reaction. So first of all, I'm asked to identify what the unknown is. So let me zoom in a little bit. It's a bit small font. Okay, so I've got a neutron plus 14.7N going to something plus a proton. So I'm going to write this as a neutron has one nucleon and 0 charge, so I'll write as 10N plus 14.7 nitrogen goes to something or other plus a proton has a charge of plus 1, so I'm going to write it as 11P plus AZX, the thing that I don't know. All right, so I need to have the bottom numbers add up. So AZX must have a Z value of 6, so 6 plus 1 is equal to 7 plus 0. So it's going to be 6. On top, I've got 1 plus 14 is 15. On the other side, I must also have to have 14 plus 1. So I need to look in the periodic table. What has an atomic number of 6? It's carbon. So the unknown is 14.6 carbon. So I need to find my initial mass and my final mass. So initially, I have 1 neutron plus I have a 14.7 nitrogen, and final I have 14.6 carbon plus 1 proton. So I need to look up, and if this were a test, you'd be given the masses. Otherwise, you can look it up online or in the textbook for the masses. So the mass of a neutron is 1.008665 U. The mass of that nucleus is 14.003074 U. And so I get a total mass of 15.011739 U. All right, final. Look up the mass of 14.6 carbon. That's carbon 14. That's the radioactive one. 14.003242 U plus a proton, which is slightly lighter than a neutron, 1.007267 U. And so I get 15.010509 U. And so now if you look at these two numbers, you can see how close they are, right? So this is why I told you in the previous chapter, don't round them off, because they're very, very similar. If you'd rounded each of them off to 15.0, you'd have said there was 0 mass difference. So never round these off. Keep all the sig figs that you can find. Okay, so what's my Q value? My Q is equal to mass initial minus mass final. So it's important to get it the right way around or you'll get the wrong sign. So my initial mass minus my final mass times C squared. So my mass difference is 1.23 times 10 to the minus 3. Very small, U. And how do I convert this to energy? Well, remember what we did. We multiplied by 931.5 MeV per C squared. So basically what you do is you just take your change in mass, multiply times 931.5, then the C squareds cancel out, and I get my energy in mega electron volts. Okay, so this is positive. So that means it's exothermic. And so energy is released. So this is a reaction that happens spontaneously. Okay, let's go on to the next example. So in part B, now I have 16.8 oxygen plus a proton. So let me write it the way I did before. So 16.8 oxygen plus a proton. So I'm going to write that as 1P, because it has 1 proton and 1 nucleon, goes to 4,2 helium plus AZX. And I got to figure out what AZX is. All right, so I have to have the numbers on top add up. So I got 16 plus 1 is equal to 4 plus A. So A is equal to 17 minus 4, which is 13. On the bottom, my numbers have to add up. So here I've got 8 plus 1. And here I've got 2 plus Z. So Z is equal to 8 plus 1 is 9. So 9 minus 2, which is 7. So my nucleus is 13, 7. And then I go to the periodic table, look up what has an atomic number of 7, and it's nitrogen. So that's my missing value. Okay, so now I want to find the mass. So mass initial is equal to, we've got 1 proton plus 16,8 oxygen. So that's 1.007267 U for a proton. Look up the oxygen, 15.994915 U. So I get 17.002182. For my mass final, it's 4,2 helium plus 13,7 nitrogen. So look up both of those. A helium nucleus is 4.002603. And that nitrogen nucleus is 13.005739. I get 17.008342. So again, you can see these numbers are really close. Don't round them off. So if I get my Q value, so it's M initial minus M final times C squared. So if I subtract the masses, I get 6.16 times 10 to the minus 3. And this time I get negative because my final mass is bigger than my initial mass. So I times 931.5. And I get minus 5.738 mega electron volts. So this is endothermic. And so energy is absorbed. If you want this reaction to occur, you're going to have to supply some energy. And usually the way that's done is by making the proton, the thing that hits that oxygen nucleus, make it have a very high kinetic energy so that its kinetic energy is bigger than what you need for the reaction, and then the reaction will occur. Okay, let's do another one. So now we've got helium nuclei going to hydrogen nuclei. So let's see what I have. So I've got on this side 3 plus 3, so 6 for A, and 2 plus 2, 4 for Z. On the other side, I've got 1 plus 1 plus, remember I'm going to say this is AZX. All right, so 1 plus 1 plus A. And the bottom I've got 1 plus 1 plus Z. So if I look at this, A has to be 6 minus 2, which is 4. Z has to be equal to 4 minus 2, which is 2. So I get 4, 2, and I look at what element has a number of protons of 2, and it's just helium. So it's just an alpha particle. So I get, when I have 2 helium nuclei joined together, I get an alpha particle plus 2 hydrogen nuclei. Okay, so now I'm going to find my masses. So mass initial is, I just have 2 hydrogen 3 nuclei, sorry, helium 3 nuclei. So that's 3.016049 U. So I get 6.032098 U. And on the other side, I've got 2 hydrogen nuclei, so 2 times 1.007828 U minus, plus an alpha particle, 4.002603 U, and I get 6.018259 U. All right, so if I look at that, what do I see? my initial mass is bigger than my final mass, so I expect that's going to be exothermic. So if I do delta mc squared, my delta m is 0.013839 U times 931.5 MeV per c squared. So again, remind you, c squareds cancel out when I do that, and I get 12.89 MeV, and that's positive, so it's exothermic. Okay, and my final one, now I've gone way up in the periodic table. I've got uranium plus a neutron going to strontium and 2 neutrons plus something else. So I've got on this side 235 plus a neutron. Remember, a neutron is 1, 0, n. So plus 1. So this is, I'm balancing my A's, is equal to 94 plus 2 from 2 neutrons plus whatever it is for my unknown particle. So I've got A is equal to, on the left side I've got 236, on the right side I've got 94 plus 2, which is 96. And so I've got my A is 140. If I balance my charge, I've got 92, the charge on a neutron is 0, is equal to 38 plus, again, charge on a neutron is 0, plus whatever my Z is. So Z is equal to 92 minus 38, which is 54. So if I go look up in the periodic table, so I've got 140, 54, element 54 is xenon gas. Okay, so there is my unknown. Figure out the masses. So my initial mass is a mass of uranium 235, 235.043932 U, plus the mass of a neutron, 1.008665 U. So I get 236.052597 U. The final mass is the mass of that strontium nucleus. So it's 93.915361 plus the mass of the xenon, 139.92164, plus 2 times the mass of a neutron, 1.008665 U, and I get 235.854331 U. So now if you look at these two numbers, you can see the difference is a lot bigger than what I had before. So I'm going to get a lot more energy either absorbed or released. Okay, so what's my Q value? Delta MC squared. My delta M is 0.198266 U times 931.5. And I get 184.7 MeV, and it's positive. Okay, so again, what I started with is heavier than what I ended up with. So again, this is exothermic. All right, so this is a nuclear reaction, something that might happen inside a nuclear bomb or a nuclear power plant, and it releases a lot of energy, and we use that either for destructive purposes or for creating electricity.